Good afternoon, students. It's your professor, Sarah Beck, coming to you from the classroom today. You've been moving steadily through your video activities for this week, hopefully. And before you watch this video, I'd like you to make sure that you've already gone back and watched the Coriolis Effect related activities and done the reading, and this will help really, hopefully, bring things together for you. So if you've learned about the Coriolis effect so far, you know that there is a difference in the northern and southern hemispheres. In the northern hemisphere, the Coriolis effect makes objects appear to bend to the right. And in the southern hemisphere, objects appear to bend to the left from the perspective of the viewer. So the example that you saw before with the paper airplane, for example, throwing a paper airplane from the equator to the North Pole, as they did in that example there, the perspective is from the viewer. So in this case, the perspective is from the person throwing the paper airplane, not, say, the person who's watching it come in. So that's an important thing to remember. It's about the perspective of the viewer or the thrower in the case of the paper airplanes. Now, what you might not quite have understood is why it's different in the two hemispheres. The Earth is spinning the same direction, the whole Earth, so why wouldn't it be the same if we're rotating from west to east? Shouldn't it be the same in both? So I want to show you just a quick demonstration as to why it is different in the northern versus the southern hemisphere. So I have this handy globe here for you. Couple of reminders of things that you've already learned. We learned back when we were talking about the seasons that the axial tilt, or the axis of rotation, is tilted. So you can see as I spin this around here that the axis of rotation is not directly up towards the ceiling. It's tilted 23.5 degrees, and that's what causes the seasons, as you've already learned. So let's get a different perspective here. I have to back up a little bit. Let's say that it is summer in the northern hemisphere, as it is right now. So what that would mean is that the axial tilt is tilted towards, I'm going to say that you're the sun. So this is summer, so we want the tilt to go towards you. So I'm going to go like this. So it's summer in the northern hemisphere. Now we can start to rotate this. You might not always remember which way the Earth rotates. Is it this way? Is it this way? But one thing that most Americans can remember is that, and as you learned earlier this summer term as well, is that the East Coast experiences the sunrise before the West Coast. Remember, we learned that the East Coast is 3 hours ahead of the West Coast. So if you're the sun, you can see that I'm passing this the right way. So here comes the United States. And so if this is the sun, if you're the sun, you can see the East Coast receives sunlight first. 3 hours later, the West Coast receives that sunlight. So the Earth is spinning in this direction. Now, another thing to remember regarding the Coriolis effect is that anyone along the equator, say you're standing on the equator in Africa, for example, you are zooming around every 24 hours at about 1,000 miles an hour. Now, if you're standing on the North Pole or the South Pole, you would just be making one turn. You wouldn't actually be covering any mileage. So the rotational velocity is 0 at the poles and greatest at the equator. And that difference in rotational velocity is what creates the Coriolis effect. But what we're focusing on right now is why it's different in the two hemispheres. So let's make sure we're going the right way. Sure enough, here comes East Coast sunrise, West Coast sunrise. So we're rotating from west to east. So now what I want you to imagine is you're no longer the sun. Now let's say that you're in a spacecraft in the International Space Station, and you're located directly over the North Pole, and you're looking down on Earth. So what that would look like, I'm going to bend this like this here, make sure that we're still going the correct way. Now you're looking down at the North Pole from outer space. Now which way is it rotating from your perspective? It's rotating counterclockwise, right? So the whole Earth should be rotating the same direction, right? But now let's try something different. I'm going to get this spinning a little faster and see what it would look like if you were in a spacecraft over the South Pole. And that would look like that. So now, looks like it's going which direction? Looks like it's going clockwise. So even though the whole Earth is rotating the same direction. It's different in the northern versus southern hemispheres based on that rotation. So again, the Coriolis effect appears to make things deflect to the right in the northern hemisphere and to the left in the southern hemisphere. Now you might wonder what's going on right at the equator. There's actually a negligible Coriolis effect right at the equator, and the Coriolis effect has the greatest impact when objects like wind or currents, things like that, are traveling over long distance across latitudes. The key here is to run into those differences in rotational velocity, and that depends on how far north or south you are, and it doesn't matter as much based on your longitude, how far east or west you are. So I hope that this video has clarified things a little bit, and I hope this has helped with the Coriolis effect. All right, have a good day.